All right, welcome back. In this video, we are going to look at, very similar to the previous video when we did ionic substances with Lewis structures and electron dot diagrams. Now we're going to do covalent. So instead of metals and nonmetals, we have all nonmetals. So nonmetal and nonmetal bonded together. And as a reminder, if you remember the ionic structures, when you do ionic structure, you have charges and we have brackets. And so, for example, Na plus Cl, maybe you saw something like this in the previous video, Cl minus 1 and plus 1. This is ionic. Ionic has charges and brackets. Now, in covalent, we're not going to use charges and brackets. Instead, we're going to show overlap. And so some teachers prefer to show the overlap. I like to teach the idea of the overlap because it shows the sharing of electrons, and that'll make sense in a few minutes once we get into some examples if you're not sure exactly what I mean by overlap. And so one of the most common ones we'll talk about, for example, is water. And so water, of course, is H2O. And so if we look up our, on our reference table, we know hydrogen only has one valence electron. We know oxygen has 6 valence electrons. So again, we're focusing on the valence electron. The valence electron is what is really important when it comes to bonding. That's really what is bonding with the electrons between the two different atoms. It's the outside element, or excuse me, the outside electrons known as the valence electrons. So when we look at our formula, we have 2 of those. And so when we look at oxygen, oxygen has 6 valence electrons. So if we draw our 6 valence electrons, we see that there's 2 spaces that are missing electrons. If we want to be able to have an octet, again, the goal is to have an octet, we need to be able to have some more electrons that come in there. Hydrogen is one of the exceptions. Instead of an octet, it has, we could call it a duet because there's only 2 electrons to meet the requirements to fill its first and its only energy level. So when hydrogen comes up, I'm going to give it a different symbol. We'll give this one an X and we'll give this one a triangle. We've now completed the shell so that oxygen now has 8. Now, I mentioned the idea of overlap. Some teachers might, want you to show the overlap because the overlap shows the area where the sharing of electron occurs. And so I usually include the electrons with their symbol. So hydrogen now is in this circle with the X and the dot. It got the dot or the 1 electron from oxygen and then had its own electron in the bond as well. Here's another one. One with a triangle and one with a dot. So I've circled the hydrogens, but we also want to circle the oxygens. I'm going to circle just the symbol with the electrons. I'm not going to circle the other hydrogen, only the oxygen in there. Now in this circle, oxygen has 8. It has the 6 original dots, and now it has the extra X and the extra triangle, representing 1 electron from this hydrogen and 1 electron from that hydrogen. The overlap, again, shows the bond. Now, in some cases, you may see answers that look just like this, again, showing the extra electrons and then showing one from hydrogen, another one from hydrogen with the triangle and then the dots. Let's see, we'll clean that up a little bit. So you may see something that looks like this without the overlap. You may even see something like this where you see the dots, and then instead of all the other dots, they just draw the bond. Now, my preference is I don't prefer this one. If I'm teaching about drawing valence electrons and drawing Lewis structures and electron dot diagrams, I want all the electrons to be accounted for. And so this is the one that I prefer the most. Okay, I prefer that one the most. And then this one would, of course, be second most because it's still showing all the electrons. It's just not showing the overlap. Okay, so it's not horrible if you don't show the overlap. New York State Regents does not require the overlap. I just prefer and show that they have that because, again, it shows a little more ownership of those electrons in that bond. If you do something like this, I believe the Regents will often accept this, but I believe that's the lazy way. At least that's my personal opinion. That's the lazy way. Okay, so that's a simple one with water. Now, again, notice the big difference between ionic and covalent. Ionic, we had charges and we had brackets, where now we have overlapping circles that take into account all of the shared electrons. Because again, covalent is sharing, where ionic was actually taking and gaining and losing electrons, where covalent is actually sharing them. Let's take a look at Another one, for example. We'll look at PBr3. Okay, phosphorus has 5 valence electrons. And if you look up on your reference table, you'll notice that bromine has 7 valence electrons. Now, if we take into account both of those, phosphorus has 5 and it needs 3 more, because again, they still want to meet the octet. Bromine has 7 and wants 1 more, but I have 3 bromines. And so if we have 3 places, that's where my bromines are going to be. And so we'll just change up the color here a little bit. Bromine is going to come in with their 7 electrons. Another bromine with 7 electrons. And then finally the last bromine with its 7 electrons. Now notice, I drew every single electron. I took into account that each bromine has 7 electrons, so I pulled all of them in. Bromine 7 purple with the 1 black from phosphorus. Another 7 purple with 1 black. Another 7 purple with 1 black. Notice my circles do not overlap yet. Okay, I have not included an overlap yet. I've only circled the bromines, basically having now the bromines met that octet rule. If we want to look at phosphorus now, I now have the 5 blacks with 3 purples. I'm going to overlap those so that they each get in there. So the original 2, and then there's 2 there, 2 there, 2 there. Now, one of the things that I didn't mention in the last molecule I did with water, another way, again, to talk about the lazy way, someone might just go phosphorus, leave its extra electrons there, and do Br, Br, Br. Again, that's very lazy because it doesn't show all the electrons. But what I want to point out, and I could have done it with the water, again, if we look at water, we'll put its electrons there and just do the H's. Each single line, remember, represents a single bond. And so a single bond is sharing 2 electrons. So one line is 2 electrons. Okay, that's a single bond. A single bond. Double bonds, of course, that would be basically like an equal line. Okay, that would be 4 electrons. A triple bond, which looks like 3 lines, is sharing 6 electrons. And so I'll draw a couple molecules just to represent that, just to make it a little bit more easy. But before we go into that, I want to talk about the Hoth Wrinkles for a minute, or the Brinkelhoffs, depending on how you've learned them in your class, but you may have heard about the Hoth Wrinkles. The Hoth Wrinkles are a set of diatomic elements that are always found bonded to another atom of the same element when they're in their pure state. So hydrogen is always found as H2, oxygen is O2, fluorine is F2, bromine is Br2, iodine I2, nitrogen N2, chlorine Cl2. They always bond together. And so this kind of gets us into some of these because some of them are single bonds, some of them are double bonds, and some of them are triple bonds. So let's take a look at the oxygen. A few minutes ago we saw oxygen and we knew oxygen is 2-6. When we look at it on the reference table, so each oxygen needs 2 more. It has 6, but it needs 2 more. So if I have an oxygen and another oxygen, and I have 1, 2, 3, 4, and then 5, 6, if we draw them how we originally drew them, what happens is we need to have some sort of movement of electrons. The electron dot structures and diagrams and Lewis structures, we can manipulate where the dots are going to go. And so we can actually rearrange this. And so instead of having my electrons just kind of spaced out, if I move my electrons and just space them out a little bit, and I actually pair these 2 up together, I still have 6. I've just drawn a little differently. I'm going to draw and represent with X's my other set of electrons for the oxygen. So now each one has 6, but when we overlap, they're going to have 8. So I'm going to have 6 X's with my 2 dots. That makes 8. And I'm going to have 6 dots with my 2 X's. That makes 8. So in the overlap, we now have 4 dots, where in the previous overlaps, we only had 2. And all the other molecules I did previously, we only had 2. And so another way to draw this, you may see it like this, with a double line. and then maybe you'll see the extra pair of electrons that are in there. Or you might just see this, double bonded O. This is the super lazy way to go. This is a little better. I think this one's the best. You don't necessarily have to have the overlap, but again, I prefer to throw that overlap in there. Now, as a reminder, and this will play a role in some of the other things, and you may have heard this in a different video or in the other notes, these electrons that are just kind of hanging out there, they do play a role in other bonding with other materials. These electrons that are hanging out and they're not bonded to anything else, they're called lone pairs. Because they're basically alone, they're by themselves. And so they're called lone pairs. Sometimes they do play a role in bonding, but basically if they're not bonded to another atom, then they're called lone pairs. Now in the previous video, the previous molecule, we had phosphorus in the middle with the 3 bromines around it. The phosphorus had 2 extra electrons on top, and then all of the other electrons were bonded in with bromine. So those were taken account for, but it did have some extras on top. So oxygen, again, is a double bond. I want to show you an example of a triple bond. If we look up nitrogen, nitrogen has 5 valence electrons if we look at it on the reference table. And each nitrogen, again, if we were to draw nitrogen 1, 2, 3, 4, 5, and another nitrogen 1, 2, 3, 4, 5, again, because it's a diatomic, so I know there's 2 of them together, each of them have 5, but they each need 3 more. Okay, 5 plus 3, of course, equals 8. So we can manipulate and move them. They each need 3 more. So the one on the left can get 3 from the one on the right, and the one on the right gets 3 from the one on the left. So we just rearrange it. I can still have my 2 over here. There's 3 electrons. Make sure we'll use this one as dots. So we have 3 that are dots, so I still have 5. And then I'll just use different symbol. I'll use the X's this time again. And so I have 5 X's and 5 dots, so I still have 5 valence electrons, but now I have the ability to make 8. So I have my original 5 dots plus 3 more from nitrogen on the other side, 5 X's plus 3 more on the right. So we could also have a triple bond like this, okay? Just with 3 lines. That's the real easy way. That's the lazy way. This one actually shows the Lewis structure, shows accountability of electrons coming from both elements, or both atoms of that element. And again, there's other scenarios where triple bonds will exist. You really need to take a look when you're doing this at the Lewis structure, at the electron configuration to see how many electrons something needs. So if we just throw something up, for example, and you'll revisit this later in the year with organic chemistry, but when we look at something like this, like C2H2, now carbon has 4 valence electrons and hydrogen only has 1, so each carbon is 2-4. It has 4, it needs 4 more. But if there's 2 of them and they each need 4 more, okay, maybe now we need up to 8 electrons, but I don't have enough. If I have hydrogens, hydrogen can only put in 1. So if we just start to try to manipulate and say, okay, there's 2 carbons bonded together, and then the hydrogens are going to be on the outside. Hydrogen can only put in 1 electron, so we'll give that an X. We'll put another X over here for that hydrogen. Then the rest is the other 4. We'll put 1 here just to start. Let's say if we had 1, 2, 3, 4. If we had our 4 dots, let's say 1, 2, 3, 4 dots. But when we look at this, we have a single one, we have a single one, and a single one. Those 2 are sharing. Okay, those are close, those are sharing. There's a pair there, there's a pair there. So the hydrogen's all done. We could even draw our circle around the hydrogen pair. But then the question is, how do we get the rest combined? We basically combine them. Those 2 are together, these 2 are together, these 2 are together. Now, that kind of looks a little messy, and so we would want to clean it up. And it would also help if you had a model kit. If you had a model kit and you only had limited numbers, you'd actually see what it would look like. And so when we just rearrange these, I could rearrange this. Here's my structure, my hydrogen and carbon. And I'm just going to bring my 3 over here. So I still have 3 dots. That was from the original 4. Remember, 4 is our valence number for carbon. And my other carbon also had 3 with 1 over here on the side and the other hydrogen. And so there's an X and a dot, an X and a dot. I'm going to have my 6 in the middle now, 7, 8 if I go around this way. So there's the octet around this carbon. I'm going to have my 6 in the middle, 7, 8. Okay? Don't want to go around the other element. I had to catch myself there. So you don't want to go around the other symbol. You only want to circle one symbol with the respective element, respective electrons. So I hope that's made some sense as far as what you need to do when you're trying to draw your Lewis structures. The key thing is look and see how many valence electrons they have. You have to represent the correct number of electrons. And then the goal is to try to make 8. You want to try to get to that octet rule. The main exception you'll see and run into is hydrogen with 2. You're probably not going to see many other examples where that is the case, at least in the covalence. In ionic, again, remember the first one that we listed with the charges, we didn't even show any of the electrons. Again, as a comparison, if you remember one of our final answers, Na plus and then Cl showed its electrons, but we often didn't show the electrons on the positive value, okay, only on the negative value. So again, key thing you need to look at, represent the correct number of valence electrons, try to figure out how they could arrange. Again, you can manipulate them. It could be a single, double, or triple bond, but one of the things you need to check at the very end, when you check each element, again, with the exception of hydrogen, which will only have 2, each element should have a total of 8. So again, we have 6 in the middle with 7, 8. I got 6 in the middle, 7, 8. So therefore, it's met its octet rule. So feel free to leave any questions or comments below, and I hope this has helped learn a little bit how to draw Lewis structures with covalent molecules, or covalent compounds, depending on how your teacher has phrased them. And so key thing is to practice. Key thing, make sure you're using your reference table. And the key thing, if you have questions, just ask, all right? Take care.